ஆன் பண்ணிட்டீங்களா? ஃபுல்லாக பேசுகிறப்பா? Okay, welcome to the video talk on digital communication, use of multiple antennas. I am Professor S.J. Thiruvengadam from Thiruvengadam College of Engineering, Madurai. At the end of this video talk, students will be able to explain the function of wireless digital communication system, explain the better rate performance of binary phase shift keying modulated single input, single output system in padding channel. Further, the students will be able to explain the concept of array gain and diversity gain in receive diversity single input multi-output system. As an introduction, wireless system designer, what are the challenges they are facing now? The first challenge is the limited availability of RF spectrum. Then the second challenge is the complex time varying wireless environment. Especially the padding and multipath are going to be the important challenge for the wireless system designer. As the need wise, from the user point of view, there is a lot of increasing demands starting from the higher data rate. Currently the LTE system offers the downlink speed of 100 megabits per second and uplink speed of 50 megabits per second. Always the user wants a better quality of service and fewer dropped calls. So the one side the challenges are there, and the other side the increasing demand from the users. Now the objective is to be on how we are going to improve the spectral efficiency. That is nothing but the ratio between the data rate and bandwidth and the link reliability. The presentation of this particular video talk on how we are going to achieve the spectral efficiency with higher link reliability. This can be achieved with the use of multiple antennas either at the transmitter or at the receiver. This can be approached in three different ways. One may be in terms of electromagnetic way of designing the antennas and antennas arrays to meet the requirements for gain, polarization, beam width, side lobe level and radiation pattern. The second may be from the signal processing point of view as angle of arrival estimation to estimate the arrival angles of wavefronts impinging on the antenna array with a minimum error and high resolution. Third is from again the signal processing point of view, but we call it as a basement processing. Here the idea is how we are going to improve the spectral efficiency, coverage and quality of wireless links with the use of multiple antennas at the transmitter or receiver at both the ends. I show some of the configurations. The first one shows the single input, single output. The second is maybe a single input, multi output. This can be thought as a user equipment as a transmitter and the base station as the receiver side as a uplink process. MISO, that is a multi-input single output. Here the base station transmits information to the user equipment, and MIMO case LTE supports the 2 receive antennas at the UE and 4 antennas at the base station. In LTE Advanced it has been increased to 8 antennas at the base station and 4 antennas at the user equipment side. This is from the single user point of view. This is in the multi-user point of view. There is a cooperation can be maintained in order to provide the MIMO configuration here. This is basically what is in practice. It's a multi-cell interference user. Okay. The use of multiple antennas either at the transmitter or at the receiver or at both ends will provide some gains, namely the array gain. This is the gain due to the coherent combining effect of multiple antennas at the receiver or transmitter or at both the sides. The second advantage is the diversity gain. This is due to the number of independently padding branches available in the channel. The third one, third one is about the spatial multiplexing. This is the linear increase in the transmission rate for the same bandwidth and with no additional power expenditure. This is possible only in MIMO system, whereas the array gain and the diversity gain, it is possible in SIMO or MISO or in MIMO system. But spatial multiplexing is possible only in MIMO system. The third aspect is because of these multiple antennas at the transmitter or at the receiver or at the both ends, interference can also be reduced. Further, I would like to mention one more point, that the diversity can also be obtained in terms of time as well as frequency. Time diversity can be given by the channel coding concept, and frequency diversity may be given in terms of the OFDM or in terms of the code division multiple access system. Now we get a quick overview or review on the single input, single output digital communications. The major blocks in the baseband digital communication system is, the first one is the source coding, second the channel coding, digital modulator, it is passing through a baseband channel, then digital demodulator, channel decoding and source decoding. Normally the source coding is mainly to remove the redundancy in the data as much as possible, as well as to decide on what rate I get to transmit the data. The techniques like the entropy, you are talking about the self-information, average information, mutual information, the coding for the discrete sources like Shannon-Pano, Huffman, Lembel-Geving. For the analog sources, we mainly use the rate distortion function, scalar quantization, and vector quantization. But these things, the PCM, DPCM, and DM can also be thought of as one of the source coding technique. These are all the things normally we studied in our undergraduate curriculum. Channel coding is mainly on the error control coding part of that. We are discussing the linear block code, cyclic code, convolutional code, trellis code, and turbo code in our normal or conventional curriculum there. Digital modulator can be thought of as in three different categories. One is about the memoryless modulation method. The second thing is on linear modulation with memory. Third aspect is on the nonlinear modulation with memory. In this particular course, mostly we will be discussing about memoryless modulation method, either by changing the amplitude of the carrier, how we are going to accommodate the modulation, or by changing the phase, or by changing both the amplitude and phase like the quadrature amplitude modulation, or by changing the carrier frequencies, that is called as the orthogonal multidimensional modulation scheme. The channel wise, mostly we are going to talk about the time variant channel in this course. This is some of the common PDF functions. Normally we used to model the channels in the baseband domain. Then the digital demodulator, we employ the correlation demodulator, masked filter, or ML sequence detector, symbol by symbol detection as the tool. And BAR is one of the performance measure. The channel decoding may be in terms of hard decision, or it may be in terms of the soft decision. This is an overview about the SISO digital communication system. Now we will look at that in specific. I would like to concentrate on the bit error rate, because this particular video talk focus on the second objective is how to decide the BER performance of BPSK modulated scheme. So this first one, this represents the AWGN channel without padding and the baseband domain. This is Y is the received signal, X is the transmitted signal. It may be plus A or minus A. W represents the noise component. It is modeled as a Gaussian distribution with zero mean and variance N0 by 2. If you calculate the error probability, this is the error probability, instantaneous error probability can be represented as Q function of square root of 2 SNR. The graph in the right hand side, it shows that what's the difference between the performance in the FSK, that is called as the orthogonal signal, and the antipodal signal, that is called as the BPSK modulation scheme. If you look at very carefully here, there will be 3 dB difference. If you look at the 10 power minus 3 as a probability of error, the minimum SNR requirement is somewhere around 7 dB. It goes up to nearly 10 dB in the case of the FSK signal. This is the comparison between the orthogonal signal or FSK modulated signal and antipodal signal or BPSK modulated signal. Now, if suppose padding is introduced in the channel, this is modeled as, instead of Y equal to X plus W, this is modeled as Y equal to HX plus W. H represents the padding component. Normally it is a complex number which has the magnitude as well as phase. Then at the receiver side, we are going to compensate for the channel distortion, that is represented by this equation. We get the, after compensation, we will get the received signal as mod H times X plus Z. Z represents the H divided by H star into W. If you look at the probability of error, this is the instantaneous probability of error. This is Q function of square root of 2 times mod H square SNR. Earlier it was simply Q function of square root of 2 SNR now. Since it is the instantaneous probability of error and the padding channel is a time varying in nature, we are computing the average probability of error with respect to the channel random variable H, which can be simplified as this expression 1 by 2 of 1 minus square root of SNR by 1 plus SNR. How do we derive this? This is basically coming from the concept of the chi-square distribution. If xi is a Gaussian random variable, then the sum of the square of the Gaussian random variables is represented as y. This is y is chi-square distributed. Now it is 2n degrees of freedom. The second one represents the typical definition of the chi-square distribution with n degrees of freedom, which we normally use to find the average probability of error in future course also. Now this function, the square root of SNR by 1 plus SNR, can be simplified like this. Finally, I would like to say that this probability of error is approximately 1 by 4 times SNR. If I am going to draw this curve, maybe in the next slide we will have a look at it. This green line represents the AWGN, BPSK AWGN. The red line represents BPSK plot padding channel. We already seen that in the presence of 10 to the power minus 3, the minimum SNR requirement was around 7 dB. In the padding channel, the minimum SNR requirement is increases up to say around 27 dB approximately. It implies that in order to get the same performance in the padding channel, we require 20 dB extra power, or we get to increase our transmit power by 100 times. This is not possible in the practical scenario. This is where we are going to use the multiple antennas to compensate for this particular requirement. The question is now, why this 20 dB extra SNR requirement or 100 times more power requirement? That is based on the deep padding, the concept of the deep padding. Okay, whenever the channel is in the deep pad, it introduces lot amount of error. How we are going to compensate this? Okay, if you look at how to count what is the probability of deep pad means, that is inversely proportional to signal to noise ratio. So it is very critical that reliability can be increased by providing more resolvable signal path that pad independently. This may be achieved either in terms of time, or it may in terms of frequency, or in terms of the spatial diversity. This is what is our use of the multiple antennas at the transmitter or the receiver or at the both the ends. இதோட க்ளோஸ் பண்ணிடுறேன், அதில் கொஞ்சம் அட்ஜஸ்ட் பண்ண வேண்டியிருக்கு. அடுத்த ரவுண்டு ஒரே ரவுண்டில் முடிச்சிடலாம் சார். Now we will look at the concept of receive diversity, because in the SISO padding channel environment, we realized that for the probability of error of 10 power minus 3, the minimum SNR requirement in AWGN case was approximately 7 dB. That is approximately, it becomes approximately 27 dB in the padding channel. Now, by the way of providing the diversity in spatial domain, we are trying to reduce the gap between these two things. So now let us assume that there are L antennas at the receiver side, L and one antenna at the transmitter. That's what I call this as a receive diversity case. Then this YI represents the received signal at the ith antenna. HI represents the channel between transmitting antenna and the ith receive antenna. X is the transmitting symbol. WI is the noise at the ith receive antenna. So it has been represented as the L different equations now. It can be combined as one single equation in vector form, like y equal to hx plus w, as y is a L by 1 vector, h is again L by 1 vector, x is a scalar, and w is a L by 1 vector. The elements of noise belongs to the complex Gaussian with zero mean and variance n0. If you find out what is the instantaneous probability of error in this particular case means, it becomes q function of square root of 2 times Frobenius norm of the vector h the square times SNR. In comparison to the fading channel, earlier it was cube function of square root of 2 times mod h square SNR. This was the expression for the padding channel. Now it has become cube function of square root of 2 times Frobenius norm of h the square times SNR. Basically, it provides an array gain of MR and diversity gain of power MR now. This can be calculated very easily with the expressions like this. This particular one, this Frobenius norm of vector h, the square SNR can be written as MR times SNR to justify that what is the gain we are getting as from the array point of view, and another one in terms of how we are going to reduce the probability of error, that is going to be here. That means in receive diversity case, if MR is the number of receive antenna, in this case I am sorry that it's L, so it is L receive antennas means you will get L times SNR and L times the diversity gain. Array gain is L and the diversity gain is L. This is the graphical representation. I have taken this graph from the book by Space-Time Wireless Communication by Professor A. Paulraj. This particular graph represents that what happened in the receive diversity case in BPSK modulation scheme. This is the AWGN curve. As expected, 10 to the power minus 3 as a probability of error means it requires around 7 dB. MR equal to 1, it represents a SISO plot fading channel. In this case, it requires almost 27 dB here, that cannot be represented here. If I am going to use 2 receive antennas here, the curve instead of 7 from this 27 dB, it comes somewhere around 11 dB here. That's the greatest advantage we are getting now. If suppose I am going to make it as MR equal to 4, it just requires around 4.2 dB here. This is the significance of providing more antennas at the receiver side. Because of this array gain and diversity gain, the SISO plot fading curve moves towards the left hand side, and that based on the number of antennas we are having in the receiver side. The thing is that the array, if it is the array gain, it moves horizontally. If it is a from one antenna to 2 antenna means because of that array gain, it moves by 3 dB. The ratio, the slope is going to be the same thing. But the diversity gain of 2 changes the slope of the curve. That means the slope is increased by the magnitude of 2 times. That implies that this is going to be a very high impact in wireless communication system. Since you are operating on the multipath fading channel, that if the number of paths are more and more, we can achieve more and more amount of the diversity gain. This is the biggest advantage of the receive diversity in the case of the wireless communication system. The question is now, if receive diversity provides array gain and diversity gain, is it possible to provide it as a transmit diversity gain? What are the requirements there? That we'll discuss in the classroom. Okay, the diversity gain increase the magnitude of the slope of BER curve. The array gain shifts the BER curve to the left hand side by the amount of the number of antennas we are giving now. If it is 2 antennas, it shifts by 3 dB. Okay, that's an advantage we are having now. And multiple antennas, assuming that the channel is known at the receiver. Okay, this is suppose a transmitter side the channel is unknown means MISO, a multiple input single output, we will get only transmit diversity. SIMO, we will get receive diversity gain and receive array gain. If it is L antennas, we will get a diversity gain of L and a array gain of L. If it is MR receive antennas, we will get diversity gain of MR and array gain of MR. MIMO case, we can get transmit diversity gain, receive diversity gain and receive array gain. If the channel is known at the transmitter, MISO provide, apart from the transmit diversity, it also provides array gain. And in the case of SIMO, it provides receive diversity gain and receive array gain only. And in the case of MIMO, we can get all the 4, transmit diversity, transmit array, receive diversity and receive array gains, provided the channel is known at the transmitter. Please, after completing this video demonstration, please complete all the assignments before coming to the class. These are all the references you can refer. First book by Introduction to Space-Time Wireless Communication by Professor Paulraj, and the second one is on Fundamentals of Wireless Communication by David C. and Pramod Vishwanath, and the third one is Digital Communication by John G. Prakis. Thank you very much. We will meet in the classroom. Sir? க்ளோஸ் பண்ணிடலாமா? முடிஞ்சது சார். இதுக்கு மேலே என் கையில் இல்லை எதுவுமே. சார் இது டைம் பார்க்க முடியுமா? அந்த ஓடும்போது எந்த டைமில் வருதுன்ட்டு?